This video is on analytical techniques. And our aims for this video are to be able to understand how high-resolution mass spectrometry can be used to determine the molecular formula of a compound, understand how infrared spectroscopy works, and to be able to interpret infrared spectra. So from Chem 1 we know that mass spectrometry can tell us the relative mass of a sample that we put into it. So if we're using molecules, we know that we might get a number of peaks. The reasons for the peaks down here you don't need to know for Chem 2, but we know that this far right peak, the highest, the peak with the highest MZ value, is the relative mass of the molecule you put in, the compound you put in. Now for both of these molecules here, C2H4, ethene, and nitrogen, N2, we can work out what that highest peak will be. And with normal mass spectrometry that we've learned about in Chem 1, C2H4 would be, if we look at the atomic masses up here, 2 times 12 plus 4 times 1. So that would be 2 times 12 plus 4 times 1, which equals 28. And N2 would be, if we take the relative mass of nitrogen as 14, 2 times 14, which would also equal 28. So if we knew that the gas that we'd put into the mass spectrometer was either ethene or nitrogen, normal mass spectrometry would not give us a definite answer of which one it was, because both of them have the same relative mass, even to 1 decimal place. So this is where high-resolution mass spectrometry comes in. And high-resolution mass spectrometry allows you to use values for the atomic masses. It gives you basically the MR value to 5 decimal places rather than just to 1. And that should allow us to distinguish between these two gases. So the relative mass of carbon to 5 decimal places is 12.01070. Nitrogen is 14.00171, and hydrogen is 1.00794. Now if we use these numbers in calculating our relative masses, we should find that our values for nitrogen and ethene are different. So for ethene, we get 2 times 12.01070 plus 4 times 1.00794, and that gives us an answer of 28.05316. And if we do the same for the nitrogen, we get 2 times 14.00171, and that gives us 28.00342. So now you can see that both these two values are distinctly different to 5 decimal places, and so with high-resolution mass spectrometry you can distinguish between two compounds that have the same MR to 1 decimal place by doing it to 5 decimal places instead. So mass spectrometry can be used to work out the MR of a compound. Infrared spectroscopy can actually be used to work out what functional groups are within a compound, and this works basically just by shining infrared light on a sample. So when we do that, basically at certain wavelengths the molecule will vibrate, and for different bonds the wavelength at which the bonds will vibrate will differ. And what you'll get if you shine light onto a sample is you'll create a graph where we have transmittance on the y-axis, and you get wave number on the x-axis. Now wave number is measured in centimetres to the -1, so it's basically 1 divided by the wavelength in centimetres, and the reason we do that is because it gives us a bit more of a value that we can understand, rather than being 1 times 10 to the -6 whatever. It's going to be 3000 or 1000. It's a bit more easy. It's a bit easy to understand. It's similar in the way where we use moles instead of mass. Moles instead of numbers of molecules for when we're doing moles calculations. On the side here we have transmittance instead of absorbance. So what you get then is when the light is absorbed, you get troughs rather than peaks, but we still call them peaks when we're describing them. So what you might get is a graph that looks a bit like this. And basically that means that light has been absorbed at these points, and we can then work out what groups are within the molecule by looking at what wave number these come out at. And so what wave number that the light has been absorbed at. Now these two peaks up here are ones that I've drawn in because they're two of the most common ones that come up in the exams. This one here, because it is like a nice rounded peak, and it comes in at about 3,300, we can associate that with an OH alcohol peak. So an OH that's from an acid and an OH that's from an alcohol will vibrate at different points. And OH for an alcohol is more rounded, whereas for an acid it's a bit more spiky. This one here is at about 1700, and this one is a very common one, and it's related to the C double bond O peak, or a carbonyl group. This bunch of peaks here are not assignable, and they're down to carbon-carbon and carbon-hydrogen bonds vibrating. And the reason why it's quite a mess is because there's so many different carbon-hydrogen, carbon-carbon bonds, usually in an organic compound. But we still can use this, and this area is called the fingerprint region. And the reason why it's called the fingerprint region is because it is unique for every compound, a bit like a fingerprint is unique for every person. And so if you have a known spectrum of a certain compound, and you have something that you may think is, say, cocaine, or a different molecule, then if you run a spectrum of the unknown compound and compare it to a database of known compounds, then you can find what it is by matching them up. So if the fingerprint regions match, that means that the molecule is that molecule, because it is unique for every compound. And it comes at about, well, below 1400, we say. So anything below 1400 is usually known as the fingerprint region. So how do we actually assign peaks in a spectrum? So in your exam, you will be given a data table which looks a little bit like this. It looks exactly like that, and you can see that different bonds are associated with different wave numbers, and so we're looking at peaks that come at those wave numbers if we've got these bonds in the molecule. So here is a molecule up here, and here's its spectrum. So we can assign the different functional groups to different parts of the spectrum. So here we have an OH group, and it's from an acid. So you'll see that we have in our table OH from acids and OH from alcohols. And OH from acid comes between 2,500 and 3,000. Now in the last slide I also told you that OH from alcohols are usually quite rounded, whereas OH from acids are a bit more spiky. And we can see here that we have a peak at around 3,000 or a bit below, and it's quite a spiky peak, and so that can be attributed to this OH acid. We also have a carbonyl group. And this comes, as you can see from the table, usually it makes a peak at around 1680 to 1750, and we can see that we do have a peak there. So that peak there is to do with the C double bond O. We can't assign anything else, but as I said, we do have a fingerprint region here, which will be unique for this molecule. So if we knew that the molecule we had was a carboxylic acid, we could get all the known spectra that we had for carboxylic acids and match them up. And if it matched this one, then we would know that the carboxylic acid we had was this one. So let's have a look at a couple of exam questions. So here we've got the following is the infrared spectrum of one of the isomers, 1, 2 or 3. So here's our three isomers of different compounds. Here's our infrared spectrum. And it says, deduce which of the isomers 1, 2 or 3 would give this infrared spectrum. You may find it helpful to refer to table 1 on the data sheet. Well, we don't have to do that right now because you can see that we've got a very distinguishable peak here, which is our OH alcohol group. It's rounded and it's at around 3,400. So we can say that if we can look at these three isomers, that only one of these has an OH alcohol group, and that is isomer 1. And so we can say that this is isomer 1. Then it says, identify 2 features of the infrared spectrum that support your deduction. In each case, identify the functional groups responsible. So we've already said that there's an OH alcohol group. So you'd say that there is a peak between the values of 3230 and 3550. So I've just basically copied that from the data table, but it's something you must say in order to get one of the marks. So there's a peak between the values of 3230 and 3550, and you've got to then say what accounts for that, which is due to the OH group. And the second feature, well, if you look at the compound, you can see that the other functional group in the isomer is a C-C double bond. And if you look at your data table that you can find in your book, you can find that a C-C double bond will create a peak between 1620 and 1680, and that's this peak here. If you look down, that's between 1600 and 1700, or between 1620 and 1680. So you'd say there is also a peak between 1620 and 1680, which is due to C-C double bond. So to get the marks for these sort of questions, you have to say where the peak is, and what I would do is say it's between a range of values and take that range of values from the data table, and then you've got to say what that peak is due to. So the first one is the OH group, and then the second one we've said that the peak between 1620 and 1680, which is due to the C-C double bond. So follow the same rules when answering these questions every time. This is a mass spectrometry question. So it says, the scientists also analysed the exhaust gases from an incinerator used to destroy waste polyethylene. Mass spectrometry showed there was a trace gas with a precise MR to 5 decimal places of that number in the exhaust gases from the incinerator. The table below contains some precise relative atomic mass data. So there we are, they're all to 5 decimal places. It says, use the data to show that the trace gas is ethene. Show your working. So the first thing to do is to show it's ethene. So all you've got to do there is basically show the sum. So you'd say that ethene is C2H4. So you're going to have 2 times 12.00000 plus 4 times 1.00794. You've got to write out the full sum and then say that it's equal to 28.037176. Sorry. So the important thing here is that you do the whole sum and don't take any shortcuts when writing the working, otherwise you will lose marks. Then it says, suggest why both ethene and carbon monoxide might have been identified as a trace gas if the scientist had used relative atomic masses to a precision of only 1 decimal place. So here you could say to 1 decimal place, MR of C2H4 equals 28.0 and MR of CO equals 28.0. And so both have same MR to 1 decimal place. The common mistake made here is that students put that they both have the same MR. They don't. They have the same MR to 1 decimal place, and it's important you make that qualification when you write your answer.